Let's talk about classifying something like the following. I'm going to classify. I don't want to. Let me think about how I can draw this thing. Yeah, I want to do it that way. So let's classify x squared over 9 plus y squared over 9 minus z squared over 4 equal to 1. So this has your typical kind of expression of, we know it's some sort of quadric surface. And just to kind of be super transparent about what we mean when we say quadric surfaces, the quadric surface, I forgot the little QR code thing. It's another awesome, great. Heather just joined us on Zoom. Heather, in case you need it, here is the link to the attendance form in 1 moment. Maybe not. I'm saying something else though. Interesting. My sticky notes are not loading. Well, if I don't have it for you, you can always go find it in the chat, in the canvas. Sorry. So just to be a little bit more transparent about quadric surfaces, these are the 6 quadric surfaces. You have an ellipsoid, which kind of has the same equation as a sphere. You have x squared plus y squared plus z squared equals something. So when I look at this equation, I can zoom in, I suppose. I kind of think of the more kind of easy version where you have just every a, b, and c all being 1. So I think of like x squared plus y squared plus z squared equals 1, or x squared plus y squared plus z squared equals 9, or some number. So that's an ellipsoid. Hyperboloid of 1 sheet and hyperboloid of 2 sheets, which are not close to each other, unfortunately. So this equation here and this equation here, I think of as being very similar. The only difference is for the hyperboloid of 1 sheet, you have 2 of the squares with positive coefficients and 1 of them with a negative coefficient. And then for 2 sheets, it's the opposite. 2 of them have negative coefficients, 1 of them has a positive. And then you got some other tricky things like the cone, z squared equal to x squared plus y squared. It's actually called a double cone because you have the top and the bottom. Elliptic paraboloid is like z equal to x squared plus y squared. And then finally, the hyperbolic paraboloid, which I'm always going to call a saddle, looks like this. It's opening, it's got a parabola going up in one direction, a parabola going down in the other direction. And it looks like z equals x squared minus y squared, or z equals y squared minus x squared. Not that there are other ways of expressing that, but these are kind of the typical ways. So those are the 6 quadric surfaces that I'm kind of imagining. Now, memorizing all that is not impossible, but it's not what I would particularly recommend. Oh, hey, Heather. Interesting. Like confusing.
I was in the wrong room and I thought it was the right.
I see. Okay. I was like, that's okay. Cool. Welcome. So, right. So I wouldn't recommend memorizing the general equations of the quadric surfaces. I don't think that's what Dr. Burke is really looking for. I think we should just try to classify the quadric surface by drawing the traces. That's usually a good idea. I would also point out that when I'm looking at this, I'm looking to see, okay, so here I've got a plus, and the minus. The minus being on the z means kind of like whatever's happening in like the xz and the yz plane is probably going to be pretty similar. And whatever's happening in the xy plane is probably going to be a little bit different. So let's see what's happening. Let's look at the xy plane first. So to do that, we're just going to set z equal to 0. And we're going to get x squared over 9 plus y squared over 9 equal to 1. Or as I would probably prefer to write that, x squared plus y squared equal to 9. So we know that in the xy plane, our trace is just a circle. There we go, finally. For the people on Zoom, there's the attendance form in case you need it. Cool. All right, so we have a circle. You don't actually have to draw the trace unless you're being asked to draw it. There's what's happening in the xy plane. Circle of radius 3. Let's look in the YZ plane. And the only reason why I might look in the YZ plane before I look in the XZ plane, although I'm going to look in both, is because I know that when I draw the YZ plane and I actually try and draw the 3-dimensional surface potentially, I know that's going to look like the flat plane that's on the piece of paper. Oh, by the way, just a quick aside, remember the problem last class where I got kind of stuck with the A, B chemistry thing? I did post kind of a write-up of that, has how it works. Really, it was easy once I figured out that y was just whatever amount of a there was still left. So we really just had to write the differential equation in terms of y. It was like dy dt equal to k times y squared. I just was not able to make my brain see that when I was in class. So if you have questions about that or want to look at that, I encourage you to. I know that homework is passed, so you might not care, but it's there to look at if you care. Okay, back to this. YZ plane, we're going to let x equal 0. And we're going to have y squared over 9 minus z squared over 4 equal to 1. And I would recommend getting used to when you see a variable squared minus another variable squared equal to 1 or some number, that should immediately set off the alarm bell. That's a hyperbola. So that's going to either open left, right, or up, down. And the way I'm going to figure out which way is I'm going to find which of those two axes has the intercept. So I'm going to draw, and I should label my axes. This is x, y. So I'm almost always going to draw a yz or an xz plane with z as the vertical axis and the other variable as the horizontal axis, because that's how we're usually drawing the three-dimensional, the whole thing together. So here, let me point out, if I let y equal 0, then I'm going to have negative z squared over 4 equal to 1. That doesn't have a solution because z squared over 4 is always positive. So negative z squared over 4 is always negative. So letting y equal 0 isn't going to give me intercepts. So I'm not going to get any z intercepts. I'm going to get y intercepts. So if I let z equal 0, I get y squared over 9 equal to 1. And we're getting y equal to plus or minus 3. And then I've got the usual kind of hyperbolic shape, which is, I don't know how, I mean, that's the way to describe it. It's a hyperbolic shape, right? They're not actually parabolas that are opening left and right. They kind of look parabolish, but they open a little wider than I would say a parabola does. So this is going to look something kind of like that. Kind of like that. So they should be symmetric to each other. In fact, while we're here, we might as well take a quick look. So just so you can see for your own self, right? If I actually want to graph something like this, I could totally graph, oops, I'm going to zoom in just yet. I wanted to make that bigger, sorry. I could graph something like x squared minus y squared equal to 1. And there's your left-right opening hyperbola. And notice how, although it kind of has a parabola look on each side, not really. Because if I graphed a rightward opening parabola, it would look like this. And that has a very kind of different look. Even if I shifted it over 1, you would still see that, yeah, those don't look quite the same. The hyperbola is a much wider opening than the parabola. So again, when you're drawing them, you probably not a whole lot of distinction, but when you're thinking about them, there should be some distinction there. And then similarly, if we look in the xz plane, we're going to get essentially the same exact graph. If we let y equals 0, we're going to get x squared over 9 minus z squared over 4 equal to 1. And we're essentially replacing the y-axis with the x-axis here. So we're really going to get the same hyperbola. It's going to look like this. Kind of like that. My hyperbolas are never, I've never drawn a good hyperbola, maybe in my entire life. They're adequate at best. So putting all that together, here's what I'm thinking of. Here's my YZ, my XZ plane. So I'm thinking this graph here is the one that's actually there. And if I take this graph and twist it 90 degrees so that it's cutting towards you, then I'm going to put that on my XZ axis, and then I should have a circle on the XY plane. So putting this all together, I have, here's my, here's my my YZ shape. And then in the X direction, 1, 2, 3, 1, 2, 3. Here's my hyperbola in the X direction, kind of coming out at you. and then also away from you. And then finally, in the XY plane, we have that circle. And if we go higher up, we're going to get a bigger circle, right? If I were to let, say, z equals something like 2, check it out. If z equals 2, I get x squared over 9 plus y squared over 9 minus 4 over 4 minus 1 equal to 1. So that's going to be x squared over 9 plus y squared over 9 equal to 2, which will be x squared plus y squared equal to 18. It's like a circle of radius a little bit bigger than 4. If we go up, we're just getting bigger circles as we go higher up and bigger circles as we go further down. So this is a hyperboloid of one sheet. So basically the difference between a hyperboloid of one sheet and a hyperboloid of two sheets is the hyperboloid of one sheet, you'll get two hyperbola, and then your other trace will be a circle. Whereas for hyperboloid of two sheets, you get two hyperbola, and your other trace will be nothing. You'll be completely missing the middle because it's kind of like two satellite dishes that are facing away from each other, and there's nothing between them. I mean, not just kind of like that. It's exactly like that. Because it kind of looks like. Sorry, why is the cursor never want to do what I want to do? Right, the hyperboloid of two sheets looks like that, where at least the way this one's written here, in the XY plane, there's literally nothing. So you get no trace. And that would be, yeah. Okay. So that's kind of the most of the whole deal with dealing with these quadratic surfaces. Your job to, if you're asked to identify one, really seeing what the traces are doing. Let's actually look at, I say that as I was about to kind of try to wrap it up. Let's look at one more, because I feel like there's one more that I think is interesting, for lack of a better word. Let's say we had z squared equal to x squared over 4 plus y squared over 4. And what's kind of interesting about this one is it almost looks the same as the one we just did. In fact, let me rewrite this just a little bit so you can see the difference. If I were to bring everything to one side, I can rewrite this as x squared over 4 plus y squared over 4 minus z squared equal to 0. And so coefficients notwithstanding, this equation and this equation, these two equations, look pretty much the same. Like, yeah, divided by 9 versus divided by 4. But really, they're very much the same, except that this one down here was equal to 1. This one up here is equal to 0. And so what happens here is this one being equal to 1 means your xy trace is something circular. Whereas this one being equal to 0 means your xy trace, well, if we set z equal to 0, the only solution there is that x and y both have to be 0. So instead of kind of bowing in like the hyperboloid of one sheet, you go straight into a point and then you get down like that. So instead of like bowing in, you go straight in, straight out. So here's what this looks like. Let's look at the traces. Trying to do this slightly faster than last time. The traces are weird here. So in fact, they're all not great, I'll just point out. So if you look in the, again, like we said, in the XY plane, well, if we set z equal to 0, it's kind of unsatisfying. If z equals 0, then you have x squared plus y squared over 4 equal to 0, which means x and y have to be 0. There is no other solution. So you're tracing the XY plane is just a point. I wouldn't graph that. Now in the YZ plane, things get a little bit interesting here. We're going to get z squared equal to y squared over 4 because we're setting x equal to 0. So this can be a little bit confusing because sometimes people miss the fact that we actually have two lines we're going to graph here. So we don't just get z equal to y over 4, sorry, z equal to y over 2. We get the square root of z squared equal to the square root of y squared over 4, which really means the absolute value of z is equal to the absolute value of y divided by 2. So meaning we actually get the line z equal to y over 2 and z equal to negative y over 2. So it kind of looks like this. let's see, z equal to y over 2. So this is y, this is z. It's like that. And the other one looks like the other way. That's what's happening in the YZ plane. So think about this for a second. All I'm going to do now is I'm going to graph the other one in the XZ plane. But what that's really going to do is going to take the same equation. If we find what's going on in the XZ plane, we're going to have really the same thing. We're going to get y equal to 0. We're going to get z squared equal to x squared over 4, which is going to come down to the same result that either z equals x over 2 or z equals y over 2. Which means you're really going to get the same graph. It's just going to be rotated 90 degrees towards you. So I could graph it again. It feels almost silly to graph it again. Yeah, same graph. It's going to look like this. I'm going to do a less good job because we've already graphed it. So then putting it all together, here's what we've got. Yeah. It's always a question as to where to put the x-axis exactly. So let's draw this in a different color so we can see it better. Here's what's happening in the. So it's really a good idea to maybe draw your x-axis at a slightly different angle, because I've almost drawn it at exactly the wrong angle for drawing the line z equals 1/2 y. I'll try to make it a little shallower here. So there's that. I'm not going to draw the bottom half yet. There's that. And then it's just kind of really rotating around. So the way to really see this would be to like pick a bigger value for z. So if I pick z equal to 1, I can see I'm getting the circle, radius 4. So I'm going to get things that look like this. Ooh, that doesn't look great. That negative x-axis there is really kind of throwing things off. And same thing down here. Yeah. I almost said, and I should have said, let's draw the thing first and then put the x-axis in there. I didn't, because I was playing fast and loose. So there's our cone, or a double cone, as I usually call it. People usually think of a cone as just being the top half of this, but it's the double cone. Cones are neat. We could talk more and more about these surfaces, but let's go ahead and move on, because we don't really do a whole lot of graphing of three-dimensional surfaces in this class or drawing them. What we really want to do is move on and talk about them as functions. So let's go ahead and go over to here. Yeah, that's good. Right. Yeah, so let's say that we have functions of 2 variables. And really, when it comes to functions of 2 variables, I like to start talking about domain. So let's talk about domain for a minute. And actually, let's go back to a function of 1 variable for a second. So, for example, if our function f of x were equal to the square root of 4 minus x, the way we would find the domain here would be by seeing that we can't take the square root of a negative number. So we're going to set the inside of that to be greater than or equal to 0. And we're going to solve for x. I don't know why I wrote parentheses there. I just happened to, because I wrote 1. So I'm going to have 4 bigger than or equal to x, or if you prefer to write the x first, you can say x less than or equal to 4. So here our domain is the set of all numbers on the number line that are less than or equal to 4. So we would probably write it as the interval notation -infinity up to +4 bracket. And we could also graph this. It's not terrible to graph. It's a square root function, but shifted 4 to the right and then flipped around. So it looks kind of like this. Where we're getting all the values of x to the left, none of the values of x to the right. We also talk about the range. And really, for a lot of these functions, the range we just look at by seeing what the graph looks like. So here the range, well, the smallest y value is 0. And then we go larger and larger and larger. So if x is 4, y is 0, and as x gets larger, y gets larger. So our range here is going to be everything from 0. Or really I should say 0 is the smallest value and you can get any value larger than that. We don't, I shouldn't want to say to infinity because we don't ever get to infinity. So what about a function of two variables now? What if we had something like f of x comma y equal to the square root of 9 minus x squared minus y squared? Let me make sure that's not the function she picked. It's a very common example. Okay, she didn't pick exactly the same one. It's similar. It's a very common example. So here's my function. And I would like to, in the same sort of way, find the domain and maybe the range. So for domain here, we're going to start with the same idea. And really, it's the same three ideas about domain that we might have learned in 17a. That you can't take the square root of a negative, you can't divide by 0, and we can't take the natural log or any logarithm of 0 or negative. So those are the things we look for when we're talking about domain restrictions. So here, to find our domain, we're going to set 9 minus x squared minus y squared to be greater than or equal to 0. And then right, because we need the insides to be greater than or equal to 0. When I'm trying to then figure out what my domain looks like, almost always one of two things will happen. Either you'll have an x squared plus y squared, and we do have that here. You could write that as 9 minus parentheses x squared plus y squared. And if you have that, you should isolate that. If you don't have that, then the other thing we do is typically just try to isolate y. Because what we're really going to try to do here is graph the domain. So here, I'm going to isolate the x squared plus y squared. I'm going to write this as 9 bigger than or equal to x squared plus y squared, or if you prefer, x squared plus y squared less than or equal to 9. And then to graph the domain, I do want to graph the domain. I'm going to graph where this equation is just equal to 9. So first I'm going to graph x squared plus y squared equal to 9, which we know is a circle of radius 3 centered at the origin. And now typically when you're graphing a domain, if a boundary is included, we draw it solidly. If a boundary is excluded, we draw it with a dashed line. Here, since I want x squared plus y squared equal to 9 to be part of the domain, I'm going to draw that circle with a solid line. But we'll do another one later where we drop the dashed line. So I'm going to draw my circle of radius 3 with a solid line. Or a solid curve, I guess I could say. And now the question almost always is, which side of our boundary do we want to include? Do we want to include all the stuff that's inside the circle, or do we want to include all the points that are outside the circle? Well, the easy way to do this is to test a point. Test any point that's either inside or outside. Don't test a point on the circle, test a point inside the circle. So a natural choice here would maybe be the point 0, 0. I'm going to make a slightly different choice and pick the point 1, 1. So there's the point 1, 1, clearly inside the circle. Is it in the domain? If you plug in 1 for x and 1 for y, does this inequality still work? Well, let's see. If x comma y equals 1 comma 1, is it true that 1 squared plus 1 squared is less than or equal to 9? Yeah, for sure. 1 plus 1 is 2. Yes. So here's what that means for us. It means that that point there is in the domain, and every other point that is on this side of our circular boundary is also in the domain. So we're going to shade in the entire interior of the circle. And that's our domain. So unlike functions of one variable, where we say that the domain is just all of some points on the number line, for functions of two variables, our domain is a set of points in the plane. So here our domain is every point in that circle, which there isn't really a good way to write, unfortunately. So here's how I would write the domain. The domain, if you really had to write it, is the set containing all points x comma y such that x squared plus y squared is less than or equal to 9. Not super exciting. It feels kind of like we might have already done that. It's much more interesting and informative to graph the domain. In fact, I can't imagine Dr. Burke would ever ask you to really do this, or at least she wouldn't ask you to do this without having first done this. So if you're finding domain, you are almost always going to be graphing the domain because that is the most useful way to think about it. I ran out of room here, so let's go ahead and move down and talk about the range. So range is a little bit more interesting. So range, actually, sure. So domain generally is set of points in the XY plane that we are allowed to plug into our function. So every point here is cool, and any point outside of there is not okay. Here's why. So let's look at the point right here. Let's say I want to try to plug in 4, 0 into my original function. It's not going to work. If you plug in 4 for x and 0 for y, we're going to get 9 minus 16 minus 0, which is -7, and we can't take the square root of -7 and get a real answer. So we're done. So this point here and any point outside the circle, not in the domain. On the other hand, the range is the set of z values, set of outputs, if you will, that the function can take on. So if I look at my f of x comma y equal to the square root of 9 minus x squared minus y squared, when you have an x squared plus y squared, I do find it advantageous to rewrite my function so that it does look like an x squared plus y squared. So I would write this as f of x comma y equal to the square root of 9 minus parentheses x squared plus y squared. And usually for the range, if we're trying to do this without actually graphing the surface, because sometimes graphing the surface can be really, really, here it's not, we can totally graph this. It's just the top half of the sphere, which is a hemisphere. But let's practice doing with that. So finding the range often becomes a quest to answer the question, how big can we make this and how small can we make this? So how big can f of x, y equal to the square root of 9 minus x squared plus y squared be? Well, to make this thing as big as possible, I need to make the thing I'm subtracting off as small as possible. All right, if I'm subtracting something, subtracting a smaller thing leaves me with more left over. So let me ask both of you, what's the smallest value x squared plus y squared could ever be equal to? Say that one time. That's actually so you're answering the other question, actually. You're answering that question, how small can I make the entire thing? And you're right. Let's go there for a second. So if I wanted to answer, how small can the function be? Then it would be the smallest when I let x squared plus y squared equal 9, and I got 9 minus 9 equal to 0, and square root of 0 is 0. So that's going to be true if x squared plus y squared equals 9, then let's say we made x equal to -3 and y equal to 0, that would work. Then f of -3 comma 0 would be exactly the square root of 9 minus 9, which is 0. And that's the smallest the square root can ever be, right? You can't get the square root of a number and end up with a negative result. Okay, but now we want to answer the other question. How big can we make the function? Well, to make the function small, we made x squared plus y squared as large as we were allowed to. To make the function big, we're going to make x squared plus y squared as small as we're able to. What's the smallest just x squared plus y squared could ever be? 0, right? You can't make it any smaller. Whatever you pick, x squared is going to be non-negative and y squared is going to be non-negative. If you add two non-negative things together, it's always going to be non-negative. And the smallest non-negative number is 0. So here we pick x equal to 0, y equal to 0, and we get the f of 0, 0 is equal to the square root of 9 minus 0, which is 3. So our range looks like the biggest it can be is 3, and the smallest it can be is 0. So our range here is all values from 0 to 3 inclusive. And we do end up writing the range in kind of the normal way, where it's just an interval notation, smallest possible z value to largest possible z value. Graphically, here's what things look like. So in the xy plane, right, if we set the function equal to 0, we know we end up getting the circle of radius 3. We already kind of did that. And then if x and y are 0, the z value is 3, and we have this hemisphere looking shape. So yeah, the range of this function certainly has a low value of, right, so in this plane down here, we're getting a low of z equal to 0. Here, here. There's lots of places where z equals 0. And up at the top, we're getting a high value of z equal to 3. And we're getting every value in between. Okay. Let's look at another example. Yeah, we got sorry, the time here, always going. Delicious. No. So yeah, let's do something like this. Yeah, I like that. Let's say we wanted to think about the graph of f of x comma y equal to the log base 2 of sure 16. I want to change that. Sorry, don't write that down yet. Or you can, I think I'm gonna change that one up. I want it to be actually x squared plus y squared minus 16. So I guess I make that, I'm annoyingly gonna make that negative 16 plus x squared plus y squared. But a more typical way to write that would be log base 2 of x squared plus y squared minus 16. Which we may or may not actually try to graph. I'm more concerned with finding the domain of the range. So for a square root, we can take the square root of a 0 or a positive number. For a logarithm, we can only take a log of positive numbers. So here to find the domain, we have to start by setting the argument of the logarithmic function, x squared plus y squared minus 16, to be strictly greater than 0. What that means for me is whatever my boundary ends up being, we're not going to end up including it in our domain picture. Here, once again, we have a boundary that's going to be circular. So we're going to have x squared plus y squared is bigger than 16, which means if we graph x squared plus y squared equal to 16, that's going to be a circle of radius 4. Send it to the order. If we graph this, I'm going to be a little bit extra careful here, because in this case, when I graph the circle of radius 4, since I know I don't want to actually include that boundary, I'm going to graph it dashed. So I'm going to graph it like this. So that boundary is not included in my domain. But one side of this boundary certainly is. Is it the inside or is it the outside? Well, the way we do this again is we test a point. So let's test the same point. If I test the point, x comma y equal to 1 comma, I meant to do 1 comma 1, sorry, 1 comma 1, which is clearly inside the circle. Is it true that 1 squared plus 1 squared is bigger than 16? Obviously not. So if you happen to pick a point that doesn't satisfy the inequality, what it means is the side of the boundary that your point lives in is not the side that we want to include in our domain. So our domain is going to be everything outside of the circle of radius 4. So our domain is the entire xy plane except for the circle and the interior of the circle of radius 4. So all of that I'm shading in red here, That's my domain. Or in words, everything outside of the circle of radius 4. My domain here is all points outside of the circle of radius 4. Centered at the origin. I guess we probably don't really need to say that, but it's good to say it. Or written more mathematically, but again, so here's the thing about writing the domain as a set. It's kind of, you've already done the work you need to do to write the domain as a set. You're literally going to take the inequality that you used to graph the domain in the first place and write it as the domain is going to be the set containing all ordered pairs x comma y such that this inequality is true. Yes, there are an infinite number of points in our domain. No, we do not write it as the set of all real numbers. It's this set with the point 5 comma 0 and 1 comma 8 and 2 comma pi and lots of 2 comma, no, not 2 comma pi is too small, sorry. 3 comma 2 pi, right? Lots of points are in this set. Infinite number. But this is the only way to express it. So it's kind of annoying. What about the range? Range is an interesting question here. I mean, I would say range is an interesting question because it usually takes a little bit of doing to figure out. So range. So I know the insides have to be positive, right? Because my domain says so. So I'm going to say for 1 second, let's say that x squared plus y squared minus 16 is just equal to some q, I guess. Let's call it q for a second. So here's what I know about x squared plus y squared minus 16. I know it has to be greater than 0 because that is required for my domain. So I know that my q has to be greater than 0. But then the insides of this can get as large as you want, right? The inside of this thing can be as big as forever and ever and ever. So the inside of my logarithm here is any positive number, which I will point out is the typical domain for a logarithmic function. So if I was trying to graph f of q equal to log base 2 of q, and q has these possible values, well, I know how to graph a logarithm. It looks something like this. If q is 1, log of 1 is 0. If q is 2, log base 2 of 2 is 1. But really, I'm just going to get the usual logarithmic shape. And since I can get as close to 0 as I want for my input, my output is going to get more and more and more and more negative. I do have a vertical asymptote here. So what I'm really seeing here is that my range is in fact everything. I can go as low as negative infinity, and I can go as high as positive infinity. I get really big by making the insides as big as I want. I get really, really negative by making the insides as close to 0 as possible. So for example, I could pick numbers like y equal to 0 and x equal to 4 point lots of zeros 1. So that the insides here are very, very small, and the logarithm of a very small number is a very negative number. Do you want to graph this thing? Kind of, yeah, okay. So let's see. So, do I want to graph this thing? I really do, actually. It's kind of a neat graph. So, I'm trying to graph this. Well, okay, I should be smart about this. I should use the techniques that we've talked about for graphing things in 3 dimensions. I should find the traces. So let's talk about finding the traces. So I've got f of x comma y equal to the log base 2 of x squared plus y squared minus 16. So let's see what's happening in the xy plane. So what am I setting equal to 0 for the xy plane? What have you been setting equal to 0 for the xy plane trace? Right, what's my z here? It's my f of xy, right? We often think of this as just being our z. So we're really just setting the function equal to 0. So we're going to say that log base 2 of x squared plus y squared minus 16 equals 0. And then if I want to solve this, 2 to the 0 equals x squared plus y squared minus 16. 2 to the 0 is 1, 1 plus 16 is 17. So we get x squared plus y squared equal to 17. So in the xy plane, our trace is going to be a circle of radius slightly larger than 4. Yeah, okay. So, yeah. So something kind of like this. Okay, not super exciting. I will also point out, since we might as well, if we look at level curves, so if we look at some level curves, I know we have other traces to look at, but give me a second. It usually makes sense to think about level curves when you're talking about the XY plane, because really the XY plane trace is just the level curve when you set Z equal to 0. But if you set Z equal to C, look what happens. I'm picking C here because I don't want to be like Z equals 1, Z equals 2, Z equals 3. I want to just pick a C value and kind of see what I get. No pun intended. So if I do that, I'm going to get log base 2 of x squared plus y squared minus 16 equal to C. I'm going to rewrite this as 2 to the C equals x squared plus y squared minus 16. And I end up getting 2 to the C plus 16 equals x squared plus y squared. So what I'm seeing here is that if I go up to an elevation of C, then my level curve is going to be a circle centered at the origin. And the radius is going to be the square root of 2 to the C plus 16. Just like it was here. Right, for this first one, when I set C equal to 0, I got a circle centered at the origin whose radius was the square root of 2 to the 0 plus 16, which is the square root of 17. So, well, so then let's look at the xz trace. So we set y equal to 0. We're going to get f of, I should just write z, James. I'm going to get z equal to log base 2 of x squared minus 16, which kind of just looks like a typical logarithmic graph with a vertical asymptote at 4. Technically 4 and negative 4. So 1, 2, 3, 4, right? If x was 4, 4 squared is 16, 16 minus 16 is 0, and that's where we get the vertical asymptote. And then we also get a vertical asymptote at negative 4. And this graph looks like this. It looks like your usual log graph, kind of, but then reflected across the z-axis. And then I really should try and do my best to not graph the other one, because we know the other one's going to have the same shape. Let's write it down, but we're not going to graph it. I'm trying to tell myself I'm not going to graph it. If I graph the YZ trace, if I talk about the YZ trace, I'm setting x equal to 0, and look, we're getting essentially the same thing. We're getting z equal to log base 2 of y squared minus 16, which I'm just switching x for y, which is the same graph. So we've kind of got this circle in the middle, and then we've got this logarithmic kind of surface rotating around it. So I'm really kind of thinking of taking this logarithmic function and rotating it 360 degrees around the z-axis to get this surface, which kind of looks like a funnel almost. So graphically, here's how I would draw it. I'm going to wait like a smart person to put in my x-axis. So I know that here's my vertical asymptotes at 4 and at negative 4. And then I've got this logarithmic shape coming up that way. I'm going to try my best to reflect it over here. It has the same look. That's okay. And then it's essentially rotating around the z-axis. So it's coming around like this. You're getting these larger and larger circles as you go up. Oh, come on. And smaller, well, I should say, not really smaller, I mean, smaller and smaller, the circles that are getting closer and closer to having a radius of 4 as we go down. So this graph kind of has a cylindrical asymptote, which is kind of weird, but it does. In fact, if you look at it, I do think it's fun. Like, I really would encourage you, if you're graphing through things in 3D, look at them on Desmos. I know you don't know, but I'm super jealous of how lucky you are to have these 3-dimensional graphing things. Like, I wish I had had this when I was a student because it's just so neat. So if you graph this, that's not the one I wanted. I wanted the 3D one. So if we graph this here, z equal to then log base 2. Can we do log base 2? I think so. We'll find out. I had what? X squared plus y squared minus 16. If we zoom out a little bit, zoom out, you can kind of see, oh yeah, there's that kind of funnel shape where in the middle, we are certainly, right, we can't get any closer than that circle of radius 4. We have this surface that's doing this kind of thing. And all right. Main range, yeah. Let me see if there's anything else I want to see here real quick. I have a couple minutes left, but let's see one more thing. Oh yeah, we should do, okay, let's look at, well, so I should point out, not everything has circles in it. There's a lot of examples of circles because they're kind of easy for us to digest, but someone could just as easily ask you to figure out, like, say, for this function, f of x comma y equal to the square root of 4 minus x squared plus y to figure out what's going on there. And so here, the domain, excuse me, I'm always starting from the same place. If I've got a square root, the insides have to be non-negative. So I'm going to say 4 minus x squared plus y is greater than or equal to 0. And now, since I don't have an x squared plus y squared, I'm going to go back to the other kind of idea, which is I usually have a pretty good shot at graphing y as a function of x. So I'm going to isolate y. So I'm going to rewrite this as y bigger than or equal to x squared minus 4. And I'm going to graph that. I should use a different color for my graph. It seems like a smart thing to do. So x squared minus 4 is the usual parabola, but shifted down by 4 units. And it does have intercepts at +2 and at -2. So here is what my boundary that I am going to include looks like. And it should be maybe slightly more symmetrical looking than I have drawn it. Okay, so that's the boundary, and almost always we only want one side of it. So I want the stuff that's above the parabola or below the parabola. Well, test a point. Test the origin. Is it true that 0 is bigger than or equal to 0 squared minus 4? Yes. Great. The point we tested is good, which means everything on that side is what we want. You could have also maybe argued to yourself, if you want y to be bigger than the function, you want all the values that are literally physically above the function. It can be harder to see if you've got like x bigger than something, but if it's y bigger than something, you can think of it literally being on top of versus below. But really, the safer way to do it is just always test the point. And then like, yeah, either got it or I didn't. It'll always work, which is great. Yeah, I guess it's not 2 o'clock. You can find the range here. It's probably going to be the same as all non-negative numbers. I can't imagine. Yeah, the range for sure. We can talk about it next time if you want, but the range definitely is everything from 0 inclusive, and then on and on and on. The way I would think about that is by letting x equal 2, and then y could be literally any value that's bigger than 0 and get any output you want. All right. We'll continue. I don't have office hours this afternoon. I'll see you all on Friday.